Good morning all. My name is Benerjee Duggineni, and I'm here going to present a term project on cost optimization of payment techniques designed using linear programming and Excel solver. Uh, Coming to the problem statement, the payment design is a complex due to difficulty in identifying the right combination of material layers to satisfy both the performance requirements and the cost efficiency. Where the overestimate of the thickness layers of leading to the higher construction and the maintenance costs. And under designing also leads to the overstressing of the payment and increase of early failures, and in the long term it results in the higher expenditure and higher maintenance. Coming to the research question, how can the linear programming be used to determine the most economical thickness of the payment layers while maintaining the essential structural characteristics? The main purpose of this project is using the linear programming to determine the economical thickness such that the we can save the money in the long term purpose. Coming to the aim to contribute to the more sustainable and economical payment design solutions. Uh, for this project, I have done a literature review and I have read a few literature and journals regarding the existing knowledge in the payment design and engineering by genetic algorithm and the particle swarm optimization, which is used to determine the optimal road payment thickness for the cost minimization. Um, and they implemented software and we implement and in this they implemented the software and compared with the conventional manual techniques in 9 road projects in the country of Iran. Whereas cost reductions does reduce up to 9 to 26.5 percentage with outperforming of PSO by 1 to 5.5%. Coming to the conclusion of the this literature, the intelligent algorithm significantly reduce the cost compared to the manual methods we generally prefer for the optimization techniques. To the methodology, we have used linear programming in the Excel solver, which is available in the add-ins of Excel. In the data analysis, we need to add that was employed to find the optimal payment thickness that meets the structural criteria at the least cost. Whereas linear programming is ideal for cost minimization in the operation research, and the Excel solver effectively manages the constraints and calculates the variables. And coming to the data is I have got the data from the research paper which detail the parameters of equivalent single axle load ESAL and the modulus of resilience MR and associate costs. Coming to the dataset overview, first DMUs, that is decision making units, represents the different payment designs, for example P1 and P2, whereas ESL stands for the equivalent single axle load, which generally measures the traffic load, which is a fixed value for all the designs. Coming to the MR, the modulus of resilience, which quantifies the material's ability to recover from the deformation, which is also a fixed value. Coming to the for the any payment, there is asphalt base, sub base thickness, which is the measured thickness of each layers in the terms of units called centimeters. Coming to the cost, the construction cost in Iran reals. Whereas I have took this data set from the literature paper, which is an open source. Where they use the currency in the terms of Iran reals. Coming to the cost improvement, the percentage improvement compared to the reference design. Coming to the SN stands for the structural number, the index of structural strength. The higher value indicates the higher the performance. Coming to the defining the decision making units, DMUs represents the different payment designs labeled P1 through P15 in the given the data set. Each DMU has a constant ESL, traffic load, and the material resilience, but they varies in the terms of asphalt base and subbase thickness as well as a cost. DMUs allows the comparison of payment designs to assess the efficiency in terms of cost and the structural performance. Coming to the defining the inputs and the outputs, whereas the inputs are given as asphalt thickness, it is one of the key factor for the surface durability and the balancing thickness. And coming to the base thickness, it is measured in the terms of centimeters, where base thickness distributes the loads to the sub base. Optimizing this thickness will reduce the material use, which is very important in terms of saving the cost and the maintenance. Coming to the subbase thickness, subbase or what the main purpose of subbase thickness is, it influences the load distribution and drainage, which is also impacts the cost and the durability of the pavement. Like if the stronger the subbase thickness, then there's a chance of a lot of durability, and we can minimize the both cost and maintenance. Coming to the cost, the total construction cost, the primary target of our target is to minimize the maintenance performance. Defining the defining inputs and outputs. The outputs are the cost improvement. It reflects the cost reduction compared to a baseline design. Higher the values indicates the greater the savings. Structural number measures the pavement strength and the durability. Higher the structural number means the better the traffic load handling. Like the more the structural number says that the more the pavement strength, which means it can handle the more traffic load. This is the given data set from the an open source, where DMUs, it is labeled from P1 to P5 ESL. It is also modulus of resilience, and asphalt thickness is given in the terms of 12 centimeters, 14, 16, 18. And coming to the base thickness, it is labeled from 15, 20, 16, and it go on. Coming to subbase thickness, it also varies, and the cost is measured in the terms of Iran Rial, and the cost improvement it is measured in the percentage, and it is and the other column is the structural number. Coming to the Excel solver implementation, I have thought of doing in the format of output oriented approach, the CCR model, where it maximizes the outputs, the cost improvements with the fixed inputs of layer thickness and cost. And the CCR model says that assume constant returns to the scale make it ideal for proportional changes in the payment designs in the inputs and the outputs. Uh, the Coming to the Excel solver implementation, the other key variables are the phi. Phi stands for the efficiency factor. Initially, it sets to 1. Higher value indicates the inefficiency, so it should be in the lower terms. So the another key variable is technical efficiency. It is calculated as 1 by 5, where its values below 1 indicates if the value is below 1, it indicates the inefficiency. And the other key variable is lambda. Its weights assigned to each DMU. Like it tells us it helps us to measure the efficiency. Coming to the objective, the maximum phi to improve the cost savings and the structural strength. And the constraints are the sum product of inputs and the weights are the less than or equal to the input value of the DMU, and the sum of products of the outputs and their weights are greater than output of the phi. Lambda weights must sum to 1. And the changing variables are phi. The increase the indicates phi. If there is an increase in the phi value, it indicates inefficiency. Model adjusts it's to improve the efficiency. And coming to the lambda, weight changes to optimize the each decision making unit's efficiency by comparing it to the others. And this project is done by using the Excel solver. By going first, we need to add in the Excel, we need to add in the solver tool, and in that we need to opt the maximum button, and we need to select the variable cells, and we need to select the solving method as simplex linear programming, and then we need to click solve. Coming to the results and discussions, efficiency analysis of 15 DMUs. Efficiency scores is range from 0.83 to 1, highlights the optimal and inefficient designs in terms of cost and structural performance. And out of these 15 DMUs, I have found that P1, P2, P4, P7, P8, P9, P10, P11, P13 are the most efficient DMUs, where the efficiency score is 1. For example, P1 is asphalt 12 centimeters, and the base is 15 centimeters, and sub base 48, and the cost improvement is 26.13, and the structural number is 4.07. Coming to the least efficient DMUs are P3, P5, P6, P12, P14, P15, where the efficiency score is less than 1. So, and this is the example where the P6 and its values. And this is the result, and I have got this by using this Excel solver. And this shows the efficiencies of each DMU. Like for P1 it is 1, P2 it is 1, which is efficient, and P3 it is 0.977, and P4 and P5 it's 0.94, it is inefficient, and P6 it is 0.83, P7, and this all indicates the efficiency of each decision making unit. Coming to the structural number is greater than equal to 3 leads to higher efficiency. For example, for the P1, the structural number is 4.07, the efficiency is 1. Compared to the inefficient, the P6, the structural number is 2.24, the efficiency is 0.83, which means the structural number greater than 3 has a higher efficiency. Structural number 2.24, which is less than 3, has a lesser efficiency with 0.83. And this is a scatter plot which indicates structural number versus efficiency. Coming to the limitations, some DMUs such as P6 and P12 have a lower efficiency score due to insufficient of asphalt and the base usage. Coming to the inconsistencies in cost improvement percentages among the higher cost DMUs suggest the variable performance related to the expenses. Absence of subbase thickness in some configuration may compromise structural stability. The main dataset may focus too much on thickness, ignoring the other factors could influence the performance. Coming to the future research, the reassess thickness specification for lower efficiencies DMUs established the minimum subbase thickness of a higher ESAL, and the evaluates the cost and the benefits of thickness investment, and to expand the data set to include the temperature effects and the traffic loads and the material quality. And it promotes the knowledge sharing among the top performing decision making units, and implement the performance specification for the real world pavement assessments, and investigates new types of materials, like how can we introduce a new type of materials like asphalt and the self-healing materials for enhancing the durability. The main project the objective is to reduce the cost by using the best optimization techniques. Coming to the conclusion, we employed the linear programming for the optimal and the cost-effective payment thickness, and we analyzed 15 DMUs, emphasizing the layer thickness role, and the higher structural numbers correlate with our greater efficiency. Linear programming enhances the payment design for the sustainable infrastructure. Future research should include the climate and the material quality variables also. Like we didn't consider these factors, but in the future we need to consider about the climate and the material quality variables. And I thank the Professor Lugao for giving this opportunity to present the project on the decision making and for the this term project, and we have learned many new things in this course. So I would like to thank him, and all my fellow classmates also. Thank you.